So this is the periodic table from your textbook, and if you compare this table here to the one from my prior video, if you notice 57 and 89, La and Ac, how they're located over with lanthanides and actinides. And I mentioned in that previous video, these are actually part of the D block. If you look at the periodic table in your textbook, if you notice La and Ac are included where they actually belong in the D block, notice they're in yellow. And the F block starts down here, starting with Ce and extends up to Lu. The table that I have over here, notice Lu and Lr are up here in the middle of the table, where again on the one in the textbook, those are located on the right hand side after Yb and No. We're really not moving anything around. All we're doing is deciding where I want to place this. The numbers don't actually change. It's 55, 56, 57 to 70, 71. So the elements themselves are not changing. It's just how we decided to draw the periodic table or how to construct it. I just want to point that out. The different tables are a little bit different about this. But if you were to count from Ce across to Lu, that is a group of 14 as you expect for the F block of the periodic table. Alright, but again, I'm not going to make a big deal about that on the exam. So the typical questions you may encounter are things like, what is the electron configuration for a particular element? And all electron configuration is basically an ordering of the different atomic orbitals needed to construct that element. Basically, how do I arrange the electrons? So we'll do this for a couple simple examples. Let's try this, say, for hydrogen. So hydrogen has one electron. So its configuration is going to be, so this is for H. Hydrogen is going to be, let me change that color. So hydrogen has an electron configuration of 1s1. And we get that because hydrogen has one electron. It's in the, if you look at the row here first, it's in the first number here for number 1. It's in S block, and it's in the first column. So its configuration is going to be 1s1. So its one electron is in an s orbital with the one electron in it. So the superscript tells us the number of electrons in the orbital. This is number of electrons. And S tells us the orbital type. And the one in front, this is the value for n, or the principal quantum number. Now, if I were to draw a diagram of this, you draw one line, and you put one electron on the line, and by convention, the first electron is written as an arrow pointing up. You might see arrow pointing up this way, or you might see double-headed arrow like this, or you might see a box with electron inside, and typically is labeled as 1s underneath. So any of these would be examples of an orbital diagram that represent this one electron in this 1s orbital. Now helium has an electron configuration of 1s block 2, 1s2. I'm going to create a new board here for this purpose, so it's easier to switch around. So hydrogen is 1s1, helium is 1s2. So its diagram would be a line with two electrons in it. One with up, one down. Now these arrows refer to something called the spin. So when it comes to quantum mechanics, we have different quantum numbers. There's the n quantum number, L quantum number, m sub L quantum number, and the m sub s quantum number. And m sub s can be plus 1/2 or negative 1/2. So the plus 1/2 represents the up arrow, negative 1/2 is the down arrow. So basically what this says is that I can put two electrons in an orbital. We know that that's max of 2 electrons per orbital. So once we get 2 in here, we're full. That's the 1s. Label that as 1s, and that's the complete electron configuration for helium. Now the next element in the periodic table, that happens to be boron. And that's going to be lithium. Lithium has got 3 electrons. 3 electrons total. The first 2 electrons have to fill the first atomic orbital. That's the 1s orbital. Now once you fill that one up, you loop down here. Now it says 2s first column. That tells us where the third electron has to go. So Li, lithium has a complete electron configuration of 1s2, 2s1. Its diagram now would consist of 2 lines, 1s, and above that now would be the 2s. We can put 2 electrons in the 1s orbital, up, down, and then 1 electron in the 2s orbital. And these are typically written as energy increases vertically. A 2s orbital is more energetic than a 1s orbital. A 2s orbital is larger than a 1s orbital. That would be the electron configuration for lithium. This continues on across the table. Let's find my periodic table. We've now got beryllium with 4 electrons. So now we'll go fill that to B, which is 1s2, 2s2. 2 electrons in the first energy level, 2 electrons in the second energy level. So its diagram will look just like Bli, except someone put 1 more electron in it. And there we go. That gives us now the configuration, the energy level diagram for boron. Notice the 2s orbital is now full with 2 electrons, which means I can't put any more inside. Let's go something a little more complicated. Once you complete the 2s orbital, look to your right. Now we're going to go left to right across the periodic table. Now beginning what's called the p block. We have boron, carbon, nitrogen, oxygen, fluorine, and neon. So now I'm going to put electrons in these orbitals. So boron with 5 valence electrons, 5 electrons total. This was beryllium, that was Be. Now I'm going to do boron. Boron has 5 electrons, so it's a 1s2, 2s2, 2p1. So I have 2 electrons in the first orbital, 2 electrons in the second orbital, and 1 electron that goes in the last orbital. So to draw this diagram, you need, 1s, 2s, and now we're going to need these p orbitals. We might recall there's 3 different kinds of p orbitals. We have the px, py, and the pz. Px, py, and the pz, and that's because of the quantum numbers. Remember, when L is equal to 1, that equals to a p orbital. M sub L equals -1, 0, and +1. That corresponds to my px, py, and the pz. So I get 3 different shapes. So we're going to put 2 electrons in the 1s. So it's 1, 2. We always start at the bottom, up, then down, up, then down. Then the p1, we can start off on the left side and put 1 in. So that would be the energy level diagram for boron. And of course, energy is increasing vertically. So when it comes to the p block, there are always going to be 3 lines. You must draw all 3 lines, whether there's an electron inside or not. Alright, so after boron, we've got carbon. Carbon has 6 electrons total. It has 1, 2, 3, 4 electrons, 4 valence electrons, but 6 total. Notice carbon ends in 2 p block, second column. So it's going to end with 2p2. So for carbon, and I lost my whiteboard. Okay, so carbon ends in 2p2. So C, oops, carbon is 1s2, 2s2, 2p2. Very much like boron, so we're adding one more electron to the p block. And my diagram will be very similar. I'll take what I already have and add one more line. Now we do not, when we fill in the p block, you have some choices. Well, really you don't have choices, but conceivably you could have done this instead. You could have put 2 electrons in the first orbital here, but that's not allowed. You cannot do that. So basically we need to fill these orbitals separately before you load the pair them up. So think of these like 3 chairs. Everybody gets their own chair first. So we're never going to double up in the p block, d block, or f block until these are all halfway filled. Alright, so after carbon, we have, I believe, nitrogen. Double check my table. It is nitrogen. Nitrogen ends in 2p3, so we'll do that. We have N, 1s2, 2s2, 2p3. Now, something I should mention here, if we were to add up the sum of these superscripts, that's the number of electrons we have total. So 2 plus 2 plus 3, that is equal to 7 electrons, and that's how many electrons nitrogen has total. So I got 2 electrons in the first energy level, 2 electrons in the second energy level. Now I need 3 electrons in this 2p sublevel, so electron goes there. So now I have halfway filled orbitals. That's for nitrogen. Once these are halfway filled, as they are right now, I'll start filling in to pair these up, pointing down. So for example, after nitrogen, we're going to have oxygen. Oxygen is going to end with 2p4. That's one more electron we have to accommodate. So electron configuration will be, oxygen will be O, 1s2, 2s2, 2p4. So 4 plus 2 is 6, 6 plus 2 is 8. That's 8 electrons total. So my diagram needs 8 electrons. So you fill in these, fill up, up, up. And notice for one, we need one more. So we'll go ahead and put that in, and that will point down. So now, as you go across the periodic table for the second row elements, it's going to be down, down, and then down. That's how this row will end.